Welcome to Introduction to Time Series and Graph NoSQL Databases. After watching this video, you will be able to explain the fundamentals of time series and graph databases, describe how time series databases handle time-stamped data, discuss how graph databases store and query relationships, perform CRUD operations in InfluxDB and Neo4j, and explore real-world use cases for time series and graph databases. As modern applications generate vast amounts of time-stamped and interconnected data, relational databases may not be the best fit for handling such workloads. Time series databases and graph databases are designed specifically for these use cases, offering efficient ways to store, retrieve, and analyze time-sensitive and relationship-based data. Let's begin by exploring time series databases. Time series databases are specialized NoSQL databases optimized for storing and querying time-stamped data, making them ideal for applications that deal with data that changes over time, such as sensor readings, financial transactions, and event logs. Some of the real-world use cases include monitoring server performance, for example, CPU, memory and network usage, tracking stock market trends over time, and logging temperature and weather changes from IoT sensors. Let's look at an example data structure in InfluxDB, which is a time series database. Each data point has a timestamp. It records when the data was collected, making it easy to track historical changes and retrieve time-based trends. The time format used in this time series database entry follows the ISO 8601 standard for timestamps. Unlike relational databases, InfluxDB does not use traditional SQL tables, but organizes data into measurements, tags, and fields. Measurements are equivalent to tables in SQL but optimized for time-based data. In this case, the measurement is temperature. Tags are indexed key-value pairs used to filter and group data efficiently. In this case, the tags include location and sensor ID, which help categorize data. Fields are the actual values being recorded, such as temperature, pressure, and sensor readings. In this case, the field value holds the temperature reading. Now, let's move on to CRUD operations in InfluxDB for storing, retrieving, and deleting time series data. The following query inserts a new temperature into the database. Insert temperature specifies the measurement, similar to a table in SQL. Location is a tag indicating the location of the temperature sensor. Tags are indexed for fast querying. Sensor ID is another tag identifying the specific sensor that recorded the data. Value is a field storing the actual recorded temperature. If no timestamp is provided, InfluxDB automatically assigns the current time. Next, let's see how InfluxDB retrieves data from a time range. This query retrieves all temperature readings from the past hour. Select with the asterisks retrieves all fields and tags from the temperature measurement. From temperature specifies the measurement similar to a table in relational databases. The where time greater than 1H condition filters data to return only records from the last hour, and now represents the current timestamp. Next, let's see how to delete old data. This query deletes all records older than 30 days. Delete from temperature deletes records from the temperature measurement. The where time less than 30D condition deletes only records older than 30 days, and now represents the current timestamp. Now that you are familiar with time series databases, let's dive into graph databases. Graph databases are specialized NoSQL databases designed to handle highly connected data by representing entities as nodes and relationships as edges. Unlike relational databases that rely on tables and joins, graph databases store relationships natively, making queries much faster and more intuitive for complex data relationships. Graph databases are particularly useful in applications where relationships between entities are as important as the entities themselves. Graph databases excel in scenarios that require efficient relationship traversal. Here are some examples. Social networks represent users as nodes and their connections, such as friendships, follows, and likes as edges. Recommendation engines suggest products, movies, or friends based on relationships and interactions. In fraud detection scenarios, they help analyze transaction patterns to detect fraudulent behavior. Knowledge graphs organize and retrieve structured knowledge. For example, Google's Knowledge Graph. Neo4j is one of the most popular graph databases, using a property graph model where nodes represent entities, for example, users, products, and locations. Edges define relationships, for example, follows, purchased, and likes. Properties store additional details about nodes and relationships. The following example represents a social media network where a user follows another user and likes a post. Username Alice and username Bob are nodes representing users called Alice and Bob. Follows is an edge or relationship showing that Alice follows Bob. Likes represents Alice liking a post. Graph databases, including Neo4j, use a query language called Cypher to interact with and manipulate graph data. It is designed to be intuitive and expressive, using a syntax that visually represents relationships between nodes. Unlike SQL, which retrieves data using tables and joins, Cypher queries traverse relationships directly, making them much faster for connected data. Cypher uses ASCII art-like syntax to visually represent relationships. Nodes are enclosed in parentheses. For example, user in parentheses represents a user node. Relationships are enclosed in square brackets. For example, follows in brackets represents a follows relationship. Arrows indicate direction in relationships. Now that you know the basic syntax, let's look at the CRUD operations. First, let's find out how to insert data. We will be creating nodes and relationships. This code creates users and defines a follows relationship. The create command creates two user nodes with property names equal to Alice and Bob. Further, it establishes a follows relationship between Alice and Bob. Next, let's find out how to retrieve data or find relationships. This code helps find all users that Alice follows. The return command retrieves the names of those users. Next, let's update the data by adding new relationships. This code adds a likes relationship between Alice and a post. Match command finds the user Alice and the post. Then, the create command adds the likes relationship. Further, let's see how to delete data or remove relationships. This code removes the follows relationship. The match command finds the follows relationship. The delete command removes it. In this video, you learned that time series databases, such as InfluxDB, efficiently store time-stamped data. Time series databases are ideal for applications that deal with data that changes over time. InfluxDB organizes data into measurements, tags, and fields. Graph databases, such as Neo4j, represent complex relationships using nodes and edges. Graph databases enable efficient querying of interconnected data. Neo4j represents entities as nodes and relationships as edges. And CRUD operations allow data management in both types of databases, ensuring flexible and scalable data storage for modern applications.